going to get started unless anybody has a question. All right. And I posted on Piazza that I'm going to go through homework 4 first. How many of you have done homework 4? All right. How many of you have not done homework 4? Well, since I posted it that I was going to do it first, I'll do it first. Kind of quick. So if you've installed Neo4j desktop, it's not immediately clear how this thing works. But when you start it up, it asks you about projects. Do not worry. I think there's either create one or just use the default one. This is a trap. It assumes this sort of people fall for this. You're going to go create an application. You are creating an application, but you're creating it outside of the desktop. So don't do that. What you do instead is add a graph and create a local graph. And then create password cannot be empty. And so you create it. Basically what's happening here is if you look at, let's see whether I can go figure out a way to display this. This is the basic structure. This case, state, sequence, component. All right, so what's that? So when you've got a database environment, you've got a node somewhere. This is a physical computer or virtual machine. In that, what's going to happen is there's going to be a process running, which is the database server program. So most of the time you don't see this on your laptop because it starts automatically. But there's a daemon, a background process on all of your machines. And so how you find this is different from machine to machine. But if you look on a Mac and you go to Activity Monitor, when you go into MySQL, you can see that MySQL daemon, that's the MySQL database server. I have not started Workbench yet. When I start Workbench, you can see that changes. So a second program started. That program, when I click on a connect, is going to connect over the network to that program. This program could be anywhere on the internet. The same game is going on here, which is there's Neo4j desktop. And then somewhere in the background, one of these processes is actually the Neo4j server. So we'll go back in and take a look at this. So anyway, so now I've got 3 graphs. When you've got a database, when you've got a server like this, there are databases behind it. So we've seen these. So in MySQL, this would be like the Laman 2017 database, or one of the other databases. So every schema you have is a different database, and it's a different set of files on your machine. In one of the lectures, I showed you how to find them. But MySQL uses the term schema and database interchangeably. Most other databases don't do that. So there's a complicated set of terminology, which is database, schema, table space, and table. In a more enterprise database environment, it's more complicated, but you can think about each one of these being a set of files or a directory. The same thing's happening here. Is there's one instance of the Neo4j server. When I create a graph, I'm actually creating a database file that's going to hold the nodes and relationships for that graph. Because this is not an enterprise version, a licensed version, this is like kind of a developer version, it will only have one graph active at a time. Unlike MySQL, where you can connect to, I don't know, arbitrarily many databases. But this is a development environment, not a deployment system. So what's happening here is you're just making graphs. When you start, it's a little odd to say start the graph. But what's really happening is you're starting a server process that's parked on the graph. And so now that that's started, if you go back in here, I don't know, you should be able to see it. I don't know what they call the process name. But anyway, now that it's started, you can connect to it. And because I made a new database, it's just, empty. So if I go in, there's no tables or relationships. So there's no nodes or relationships. When you run the template for the final exam, so if we go back and we look at the template that I gave you for the final exam, I think this is it now. Yeah. You can see there's a bunch of things that test the environment. You'll notice when you get to Neo4j and you try and test it, it prints out a bunch of stuff about people, like Tom Hanks. And that's just because you can see I'm actually going in there and saying, can you find the person Tom Hanks? If you don't install the movie database, it's not going to find it, and it's going to return an error. So if you're trying to do the final and you get some kind of weird error, it may be because the movie graph is not running, it's not been instantiated in your database. And for reasons that are not particularly clear, when I run this test, I actually cache that data in Redis. And so you can see I basically have the answer that comes back, and then I put that in Redis, then get it back. So the Redis test will fail too. So if you're having that problem, all you just need to do is jump into code, create a graph, go to the second one, and if you click that, it'll make the movie database. And so you will not get weird error messages. You don't need the movie database for the final exam, but the sample code that I give you to initialize the environment assumes it's there, and so you will get weird errors. But if you don't find it, so if you get these strange errors, that might be why. So anyway, that's how if you're having trouble like getting your graphs going, the way you get them started in desktop is much different than the way you got them started in Community Edition. Most of you have downloaded desktop. And you basically have to open desktop, create a project, create a graph, and then connect to it with the browser. So if you're having trouble getting the Neo4j environment set up, that's what you need to do. So is that clear to everyone? Outstanding. So we'll start with Redis because that's the easiest of homework 2. Sorry, of homework 4. I gave you this file, which is a bunch of functions that you can use to do the Redis part. There's a little bit of a trap in here. The version that I gave you used a function in Redis called HMSet. It stands for hash set multiple. When you go and take a look at the Redis documentation, or you go back and look at the lecture notes, so like go Redis types, the data types in Redis. There's strings, which are just what they sound like, they're character strings. Lists, which are basically Python lists or Java arrays. There's a bunch of operations on them, but basically you can push something to the end of the list. You can push something to the beginning of the list. You can pop something off the list. You can find the number of things in the list. There are sets. So lists pretty much mirrors the Python list, or in Java that would be an array. Sets mirrors the Python sets. It would mirror a set, one of the template set classes in Java. There's hashes. A hash is basically how you put like a dictionary, so a Python dictionary. So the hash has got a name, and then what's inside the hash is basically key value, key value, key value. So it is the Redis equivalent of either a Java hash map or a Python dictionary. And then there's a bunch of other ones. If your queries were only ever going to return a single object, so you were only doing find by primary key or retrieve by primary key, whatever we called it, by and large, the map, HMAP would work just fine because what you're getting back is a single dictionary. The problem is that if your query returns more than one thing, you're getting a list of dictionaries. So what you're getting back is an array of dictionaries. So the return type for any query in REST relational is a list. It's an array. And instead of the list support in Redis is kind of limited. So instead, and the map will not support an array. So all I do instead is to add it to the cache, it's given a key. It is given some structure. So this can be pretty much anything. What it does is it takes that and dumps it to a string. So it takes the data structure and dumps it to a string. And then it uses the standard set. So for this key, the data is this string. The term for that's called serialization. You're taking a complex data structure and you're just converting it into a string. And then you do the inverse on the way out, which is if you're asked for a key, you go and get the string associated with that key. If one is returned, then you take that string and deserialize it back into whatever the data structure was. So if you take a look, let's go into applications, utilities. Terminal. Let's see whether I can make this bigger. All right, so Redis appears to be running. We have other ones running. That's the Jupyter Notebook. That's the Redis server, so what the heck is that? We'll go make a new shell. Make it a little bit bigger. To Redis CLI. So I'm connected. You can do this test here, keys. That basically returns all the keys that match that pattern. So you can see there's a bunch of keys in here. I'm going to make this a little bit wider. If I take that key and I go get on that key, so I'm going to get on that key. You can see that I get back a very long string, but you can see that that looks like an array of results that's been converted to a string. So that's all that is happening is because Redis doesn't support anything other than simple data types. If you want to put an extremely complicated data type in there, it's a very common thing to do to serialize it to a string and then deserialize it. That'll sound wonky, which is a highly technical term. But if you go back and look at homework 2, which I'm sure has just been blotted out of your memory as a painful experience. If you go back and take a look at homework 2, and you go find one of the functions, so it's resource primary key. So this one is the one that'll do a query. So you can see I do a data service retrieve by template, resource name, query template, the fields, limit offset. This is exactly what we're modifying with Redis. So this would go, and the modifications we're making would go in here. But you can see that before we send the result back to the client, we also serialize it here. Because anything that goes over the web is a string of bytes. So the way you pass a complicated data structure over the web is you pass it as a string of bytes and then something that tells the recipient what it is. So if this is homework 2, I think this is it. If I go run this, all right, you can see this thing is listening. But if I go into Postman, which I gotta go start Postman, obviously. If I go start Postman, which is just something that sends REST requests. We'll actually just do it this way. We'll go into the browser first. If I do in here API, so that's people, question mark, name last is equal to Williams, and I run that. When did I get an error? So what was the error that I got? Name limit is not defined. So I was screwing around with this apparently. Anyway, what'll happen is, just give it a limit then. I can't give it a limit, but basically what'll happen is you'll get back a character string it's going to come back as text. The way that it gets fixed in a real system is the headers, the response headers will tell it what type it is. So there's a content type. And that way the recipient knows that the string should be converted to JSON. Yeah.
I have a question on that. The cache function.
Yeah, we're going to get to that.
Okay.
But anyway, so it's the same game that's going on, which is if you go and look before I send it over the web, I JSON dump it, because the web won't handle a complex type either. So that's the one conversion you need to do, is to just take the HM set stuff and replace it with this code. If you want to take your family photograph now, you can, just in case you want a copy of it.
So your first template to cache function.
It doesn't matter. It doesn't matter. I don't use it for anything. So I gave you this function to compute a key. If you remember in homework 2, I gave you some kind of path like this. So it was basically people, question mark, blah, blah, blah. So it took a resource name, a query template, and a set of fields. So that came in as a string in the base of the URL, and you had to convert it to the resource, the JSON template, and the fields. All that's going on here is you're doing the opposite. So if I give you a resource, a query template, and a list of fields, this is going to return that as a string. So it's almost exactly the reverse mapping from homework 2. Homework 2, you took the string version and had to convert it to a resource name, a query template, and a list of fields. This is the other way around. If I give you a resource name, a template, and a list of fields, you just have to convert it to a string. And so when you go back to the Redis command line, if you take a look at this, you can see people, and instead of using question mark, I used colon people. That's the query template, right? So this person, his name last is Williams, throws writes, and then that's the list of fields. So that uniquely defines a query. So what I do is I just take this, that's the resource name, convert that to a query template, convert that to a field list. So that's the mapping that's going on here. And so I gave you this function because it was kind of tedious to do that, because it was just a bunch of string manipulation. So you can just use that function. If you look, I then gave you the templates of 2 things to implement. This one actually has the implementation, so you're supposed to implement these, but each one of them is just 3 lines of code. And so this function is a request to check the cache. It is given a resource, a query template, and a list of fields. It's going to take those and convert them to a key. It's going to look in the cache for the key. If that key is in the cache, get from cache is going to find the value and convert it back into the original data structure and return it as a result, and then you return the result. So that's adding it, and that's getting it. They're just completely symmetrical. So compute the key, get it from the cache, return it, compute the key. This is the result. So this is a result of that one, that retrieved by template, go stick it in the cache. So these 2 functions in aggregate are just 6 lines of code, 3 in each of them. And then the only other thing you need to modify is you just go into data service. This is the data service function. The very first thing you do is R is equal to, I called it Redis, what did I call it? Data cache. yeah, data cache dot check query cache, and it's going to want the table, the template, and the fields. So that was the function we were just going through. If R is not none, and the length of R is greater than 0, print cache hit, turn R, print cache miss, and so you just go and can call check query cache, which is going to build a key that can find the string that deserializes and returns it. If not, you're going to keep going. You'll notice down here that I actually mess with the input variable fields. In general, that's not a good practice. This is an input variable. It's a pointer to something. It's not a good idea to screw around with a pointer to something inside a function because you're changing the thing outside of the function. I was just lazy. So what I should have done is made a copy of it and mucked around with a copy, but not actually muck around with the original one. Python allows you to have those side effects other languages don't. So since I muck around with that, I just basically have to go original fields, make a copy of it. Oops. Make a copy of it. So I just make a copy of it. So I'm going to have the original one. And then when I get down here, I have a result of the query. I just go data cache.add, add to query cache, and I give you the table, the incoming template, and the original fields. And so that's just going to add it to the cache. So to do the Redis stuff, you basically need to just put this in the beginning of retrieve by template and put that at the ending of retrieve by template. So it's like 6 or 7 lines of code. If you go back to the unit test for this, so this is the unit test for the data service. I have a template. I'm going to go change this template. Name last Williams, throw is right. That's left. And these are the fields that I want. This just says call the data service and retrieve by that template. So go to people. That's the query template. That's the fields. Dump the result. So I'm just going to do this twice. And you can see the first time I get a cache miss. I run the query. This is the result that comes back from the database. I stashed at it as a string in the cache. The second time I get a cache hit. So you'll notice I don't run the query or do anything else. So that's literally all you need to do for the Redis part. Part of the reason, I think I demoed this in class, but I didn't, I'm not sure that I did, is on simple queries, it's in samples. I don't know which project it's in anymore. Data cache, unit test. Data service unit test. So you can see that this function here runs a comparison. So you give it a resource, a template, and a list of fields. Right? And for 1,000 times, it goes and calls test get resource, so it will get the resource, but it doesn't use the cache. That's just a flag I added. And then the next time, it does it again for 1,000 times, but does use the cache. And so if you go, and I'm just going to modify this so that the template is different. I don't know, RBI. So I haven't looked this one up before. If I do test one, and I run this, okay, so it's running a different one. Don't know why I did that. But you can see that what I do is I run it without caching. So I go run it without caching. This is the result that it provides. You scroll to the bottom of this. A lot of people named Smith. Right. You can see that running that 1,000 times. No, I didn't print it out. Now it starts getting the cache hits. But the ratio of speed up is a factor of 7. So using the cache is 7 times faster. And that's a relatively simple query. If the query were more complicated, like if it were going through views and things, the speed up would be a lot better. But you can see that it speeds it up by about a factor of 7. The other reason that you do this is if you go back to the original. So what's really happening here is there's one application here. I don't know what to call this. This is just the website application. So when this gets a request to look something on a URL, it's going to call the database and get an answer. But there may be another application in here, which is, and it's not likely in a baseball database, but this is the thing that's supporting the ATMs. And so there's a huge number of ATMs out here connecting to this, and then this is your website. These two different applications are going to send requests to the database. They're going to contend for resources in the database. Websites have very high traffic. And so by putting the Redis cache on the side and checking that, just going to move these things. Oops. This look aside here, the path is going to be the request comes in, you check the cache. If you get an answer, you return it. Otherwise, you come through to the database, get the answer, stick it in the cache, and then on the way out, you return. This look aside stops all the web requests from coming into the database. So in addition to making these requests faster, it also stops them from interfering with the other ones. So the speed above 6 is pretty impressive, but even more important is that it is offloading function from the database that might interfere with other applications. This is by far the most common use of Redis is a look-aside cache. Because a request comes into a service, a microservice. Microservice determines whether or not it's computed the answer. If it has, it returns it. Otherwise, it does the work. So I would say about 80% of Redis use cases are this kind of look-aside. And basically, if you just go Redis web cache, and you just pick some technology node, you can see that there's all kinds of documentation about like how to build an API cache with Redis and Node, which is exactly what we're doing here, is we're caching the result of an API. So it's by far the most common use of Redis. There are other ones that have emerged, but that is like the Redis use case 101. So that's why I asked you. What you literally did is you can now put, on your CV that you did an API cache to offload SQL queries from a database, and you connected that cache to a microservice to get a 10x improvement, or some other ones. If you need me to give you the buzzwords for your CV, let me know, and I'll just put it in an email for you. But you've done the most common use case of Redis, so that's why I had you do the Redis one, because that is by far the most common use case. All right. So now we're going to go to social media. Sorry, the graph. All right. This is going to load the players. So that's the first thing we're going to do, is we're going to load the players. So that function selects the player ID, the last name, and the first name from the people database. And then there's a clause here, which is if that player ID exists, and select star from appearances where the player ID is the same and the year is greater than 2010. I gave you 2017 so that you don't get your data, but your node database too big. But what's happening is this select is only returning people who appeared in 2017 in your case. So you will only add this information to the database if the person appeared in 2017. If your queries are if your load queries are running slowly, it probably means that you don't have an index on appearances, because you may be using LAM and raw. So all you need to do is to just go add an index on player ID and it'll speed it right up. So if you get into the situation where it's starting to run, but the query's running slowly, it's because you don't have an index. So step one on this is just go down here. Now there is a bug in this. I mentioned this on Piazza. It's really not a big deal, but if you notice, cursor fetch 1, when you run a query, what you get back is a cursor on the result. Up until now, we've always done fetch all, get all the results that the cursor is parked on. In lots of queries, that's a really bad idea, because the cursor returned 3 billion rows, and you don't want them all at once. So there's fetch 1, and then there's fetch n. So what this says is get the first one, and then go through and do something. But you need to make sure that the second fetch is done at the end of the loop, because in the code I gave you, it does it when it enters, and that means you effectively skip the first one, because you run fetch 1 and then another fetch 1. So it's just a minor bug. If you go look the code I gave you, right, the fetch 1 is up here. It's got to get moved to the bottom of the while loop. So we're just going to load the players. and I'm in, right? So we're just going to go load the players. And so you can see it's just going through and loading the players. Mine is going to run longer because it's loading everybody after 2010. So I returned 3,057. I think yours returns about 1,300. You do not need to change it to 2010. And just comment that out. Now I'm going to load the teams. 34 teams. Yours will return 30 teams, not 34. Because there are some teams, since I'm going back in time, teams sometimes move from place to place and their code changes. So I've got 4 teams you don't have. And then load appearances. If I run that. So this one runs a little while because it's basically doing a huge number of appearances. This is the one that might run really slowly if you don't have an index on appearances. So you can either put the index on or decide to take a nap. But it might run for a little while without the index. You can see even with an index on mine, it does run a little slowly, mostly because I'm doing I/O. Basically, print statements are I/O, and I/O is expensive. And I'm loading lots of ones that you're not loading. So this is just going to go on for a minute. The nice thing about software in general is that if it's going to fail, it usually fails quickly. So you're in this situation where nothing good can happen, which is if your program runs fast, it means it failed. If your program doesn't fail, you spend most of your life sitting here watching it run. So there's no way you can win, because it either doesn't work or you just get to sit here and watch it. So it's going to go for a while. Well, I'm not going to debug. And I don't know why you would dump add to cache string. We'll deal with it later. So put 11,455 records. So if I go back to my Neo4j, that's WebStorm. If I go back to my Neo4j, go into the browser, and I can just get rid of this. You can see that I've now got, I'm loaded the movie stuff, but I've got player, team, a bunch of other things. If I click on appeared, and I return something other than 25, you can see that I've got a much richer appearance graph because I've done multiple years. Since you're doing a single year, you'll never get into a situation where you have more than one link between a player and a team. But I did this for every year. And the reason that I did that is that in my case, there are properties on the relationship. So I can actually go in and say, all right, there were 4 games in year 2013, sorry, 2016 between these 2 players. The reason that you do that in general is a very common computation is shortest path, but another common one is weighted path. So I might want to actually go and use some number on these edges as a weight. So I want to have the least weighted path, because for instance, it could be distance as an example. So I don't want the shortest path. I want the one with the smallest weight. But I didn't ask you to do any of that. But my appearances are going to look a lot richer than yours for that reason. And then you just go back in. I'm going to load the fans. These ones are quick, and they don't print anything because they're unlikely to fail. because they're just making new data. They're not loading lots of data out of the database. So just do that one. And then I comment that out. And I'm going to create supports. So if I go back into Neo4j and I close these out, you can see that I've got some new relationships, follows, and supports. If you run your program and don't see it immediately, there's a timer loop here. So every certain period of time, it goes and retrieves all the metadata. So if you don't see it right away, it might just be because the browser's not refreshed. But if you do this a couple of times, it'll cause it to refresh. But if I go back in here and click supports, this is my graph of who supports which teams. So you can see that Abraham Lincoln, because he's from Illinois, supports the Chicago Cubs and the Chicago White Sox. James Madison supports the Yankees. He's not a very good person. George Washington, not surprisingly, supports the Washington Nationals. And John Adams was from Boston, so he supports the Red Sox. Then you can see there's a follows relationship. So Thomas Jefferson and James Madison both follow George Washington. So that's kind of the initial data that gets loaded. And so now it's time to actually, that's all just part of the setup. And now it's time to actually go and start creating things. So the first function I asked you to implement was create comment. And I give you a fan ID, the comment string, and then a team and a player. So when I go into the template to implement it, and I'm going to go create a comment, I basically do the following. You don't have to do this, and I wouldn't take points off for it if you didn't, but I do the following. If the uni's none, so they did not give me the ID of a fan, or the comment string is none, they didn't give me a comment, or the team ID is none, and the player ID is none, I raise a value error. Because I don't have something I need. The comment connects two things. So I need a fan who made the comment. I actually need the comment string, and then it's got to be on something. So if I don't pass this condition, it's bad data. So if I get here, I at least have been given something that's meaningful. And I'm just going to say the fan node is none, the team node is none, and the player node is none. I'm just initializing it because old people like to initialize things, because when we learned to program, things were not initialized to null for us. And so rockets crashed into the ground and stuff like that. And I'm just going to go self.graph. It's create transaction. I have to go look at the actual. So it's homework 4. So what is it? No, it's over here. Homework 4. Over here. It's homework, so it's homework template old, social graph, and comment. It is going to be tx begin. And so what I'm going to do here is I'm just going to basically go and begin a transaction. So I'm going to go begin a transaction, but I am not going to auto commit. Databases, most databases support something called auto commit, and on most databases, it's the default. And what that means is that if I send the database a command over a connection, it'll run the command and then run commit. It always does it. But I'm going to be making multiple updates here, so I don't want to do auto commit at the end of every one of them. I want all of my updates to happen or not. And then I'm just going to go try. I'm just going to put a pass here for now. I'm going to do except exception as E. And I'm going to say print exception is equal to E. Something bad happened, so I'm going to basically roll back, which means I'm going to undo any changes that I made because it failed. And then I'm basically just going to re-raise the exception. Because I caught it here, I don't want to mask it. So I'm just going to re-raise it so that the caller knows something bad happened. So the bulk of the work is in here. So the first thing is fan is equal to self.get fan of the uni I received. So you gave me a uni string, a uni ID. I need to go get the node in the graph. If F is none, I have to raise that value error because despite the fact that you gave me a non-null uni, there's no node in the graph with that uni. So the string was valid, but there's no corresponding data. And then I go if team ID, if you gave me a team, right? So it's there. I'm going to do the same thing. T is equal to self.get team, right? And I'm going to give you the team ID. Then I'll play the same game here. If T is none, I'm going to raise a value error. And then I have to do the same thing for player ID. So if the player ID is not none, you gave me one. Right, I'm going to say go get the player. Right. I'm going to call it P. If P is none, you asked for a player, but I couldn't find one. I'm going to raise a value error. So now I'm ready to go. So the first thing I'm going to do is I'm going to say the new comment is equal to a node. Right. The type of this node is comment. And the comment is equal to what was ever passed in. Now, I wanted to give these things IDs. So what I'm going to do here is I'm just going to go comment ID is equal to UUID, UUID4, and then I'm going to convert it to a string because Neo will not store UUID because that is a class in Python. So I'm just going to convert it to a string. Somebody asked on Piazza, the comment IDs don't make any sense because like it assumes if I'm going to create a sub comment, like how did I know the comment ID and what's going on here? And that is because all of this stuff would be behind the user interface. If this were some type of web UI, whatever I was displaying you know, I'd click on this and I'd say add a comment to that or something. Under the covers, I would get the ID to do the work, but I would not expect the user to get out a piece of paper and a pencil and write down a UUID. It's just part of the internal implementation. So I'm going to go make a UUID, and I'm going to set the comment ID is equal to the comment ID. So now I've made the comment in my client program. So if you remember, if you go back to my example, right? This is my program. That's the database. I've got the node in my program. I've got to push it to the database. So now I have to go push it, and the verb for that is tx.create, and I give you the comment. How did you know that was the verb? Because I gave you an example like of how to create a player. So go make a node. In this case, I'm making a comment. The label's comment. Those are the properties. Go write it. So that's going to go stick the comment in there. And then if the team is not none, so I did find a team, I'm going to go and say, well, before I do that, I have to do one more thing. I'm going to say my first relationship is equal to a relationship. The source is fan. The type is comment by. And the target is the comment that I just made. And so now I'm going to go put that relationship in. So that's how I've linked, bless you. That's how I've linked the fan and his comment with the comment by relationship. If T is not none, I go R2 is equal to relationship. And this is a relationship from the comment. It's a comment on relationship. And it's a comment on the team. And then I go create that one. And then I go do the same thing for player. So if the player is not none, I go make another relationship. And that's comment on the player. And then I go push R3. So at this point, I made the comment. I connected the fan to the comment. If there was a team, I connected the comment to the team. And if there was a player, I connected the comment to the player. If I got here, I'm just going to do tx.commit. I'm going to commit the transaction. If I get an error, I go back and roll back the transaction. And that's all you really need to do to create a comment. So go back to the unit test. This stuff here was just me fooling around, testing things like get team and that stuff. You don't really need to do that. All you really need to do for the create comment is the fan ID is John Adams. Comment is awesome. The team is Boston. And you cannot use this one because Kevin Euclid didn't play in 2017. So you might get an error if you try to do that. The easiest thing to do is just basically go and say match P comma player, return P. It's going to give you a bunch of players. Just pick one of them and use that ID. That way you know that player is in your database. I'm going to go pick a specific one. So I'm going to say where last name is equal to Pedroia. And I'm going to spell Pedroia properly. And I'm going to return it. Oops. Yeah, I have to tell it which node I'm talking about. So I'm going to go down here and just basically say we're P dot last name. That's Dustin Pedroia. I just copy his ID. So I'm just going to put it in here for now. I'm going to say I'm just going to copy his ID. All right, so I'm just going to go here. And I'm going to go team ID. It's equal to Boston, because I can never remember the order. The player ID is equal to Pedroia. I can get rid of all this stuff because I don't really need it. It was just me testing the get functions. And then I'm just going to return C or print C. And I was kind of sloppy here. In general, if you're going to do testing, it's considered customary to put the calls to the tests at the bottom of the file. So there's a single place where you can comment them out. So I'm just going to call test create. I'll run it again. You can see that it returned a node of type comment. The comment was awesome in the comment ID. So if I go back into my graph and I run that query again, it's going to give me back Dustin Pedroia. If you click on a node, you'll see that funny little thing down there that looks like a graph. If you click on that, it expands the graph. And so you can see here that this is the little cluster that was created, which is this comment is on Boston, and this comment is on Dustin Pedroia. And these are just the appeared relationships that only be one in your case. And then if I go and expand this, it'll show you who made the comment. So John Adams made this comment. So comment by, comment on, and then you just have one appears here. So that's what yours would look like. Create sub comment is literally almost the same logic, so I'm just going to copy it. And it's just a little bit different. So it's going to have a uni, an origin, comment ID, and a comment. So the uni can't be none, the comment can't be none, and the comment that I'm commenting on can't be none. So in this case, the check is simpler. I'm responding to a comment. I have to have the person who's doing it, the comment that I'm responding to, and what they're saying. So I'm just going to go in here and say the fan, the original comment, are none. I'm going to go begin a transaction.
Do you mean is none?
What?
Origin comment ID.
I'm going to deal with it in a second. So, no, it's uni, origin, comment ID, comment, uni, comment is none, origin, comment ID is none.
Yeah, you wrote is not none for origin comment ID.
Yeah, sorry. All right. So I'm going to begin it. I'm going to go make a comment ID just so it's a little clearer. I'm going to call it the new comment.
You mean none for all of them, right? Sorry.
Just give me a second.
Mm-hmm.
So if the uni is none, or the uni is none, or the comment is none, origin comment ID is none, so that should be the test. All right, so this is the new comment ID. So I have to go get the fan like I did before. And then it's the same thing here. I have to get the comment. And I gave you the comment. I give you the original comment ID. If the comment is none, I'm going to raise a value error. So now I have the fan and the comment. I'm now going to make the sub-comments. Sub-comments are just comments. And so it's exactly the same structure, which is it's a comment. This is the message, and that's the comment ID. This is the ID of the new comment. So I'm just making a new comment, and I'm creating it. Relationship 1 is going to be response, or I'll call 2, response by, I don't remember what I called it anymore. Response by, yeah, it was response by. So this fan response by that comment, create R1. I don't have to, I would not necessarily have to do the null checking because I would catch it in the exceptions, but that's the way old guys program. R2 is equal to relationship. And it is, no, it's not going to be C. So that's going to be C. It's going to be C is a response to the original, what do I call it? All right, so now I overrode C here. So that's the new comment. Oh, that's the original comment. So old C is the old comment. New C is the new comment. I'm going to make it. I'm going to go do this. It's the new comment. Let's see. New C, and then new C is a response to old C. And then I'm going to command, so let's just double check this. So I get the fan, I get the old comment, make the new comment, and then I say the fan, this is a response by to the new comment, and then the new comment is a response to, and then I do R2 and then commit, otherwise I do an exception. So then to test this, I'm going to go test create sub comment. I don't need to get it. I was just screwing around. So that's the comment that I'm responding to. The message is great at walks. So George Washington is going to create a sub comment on that. And then I just return it. I'll copy this out. Comment that out. And if I didn't make any mistakes, I'll just go run it. And we'll go see what happened here. So we'll go minimize this. And we will go response 2. All right, so you can see this is a response to that. If I expand that, you can see that was John Adams was commenting on these. So John Adams commented on that. John Adams commented on this. Then if I click on that and expand it, you can see that George Washington responded to this comment. So he made this response by, response to, and then this is the original comment. So you can see creating comments and creating subcomments is basically the same. Part of the reason that you do graphs is, when I'm trying to determine what to show John Adams, like what recent comments to show John Adams, I just go find out who he follows and then see what comments they've made recently. That'd be an example of what you do. And then the final thing that I asked you to do is get the comments. So given a player, go find the comments on the player. To do that one, I'm actually just going to basically go and change graphs. So I'm going to stop this one and start this one. This one's going to take a second to start. So I'll go to the browser, get rid of this. Okay, so that's not the ones I'm looking for. So I'm just basically going to go and say, just going to go get the comments. So you can see that in this one, there's a lot more comments. Now this looks a little weird, but if you expand this, you can see that there's a person, and then if you go expand that, you can see that it's commented to a bunch of things. By the way, don't ever be drinking or use LSD when you use this interface, because it'll really freak you out. Not that I know. All right. So you can see I've got a somewhat richer graph. The query to go figure out comments is go figure out comments in a player is, I'm just going to go find a player. So that's Pedroia. Should be another player in here somewhere. Well, maybe not. So I'm just going to go get his ID. And the query to do that is match any node the relationship has got to be comment on. And it's a comment on P, which is a player, and the player ID is that. And then I'm just going to return P, comma, R, comma, N. And so you can see that there's two comments on Drust and Pedroia. If I wanted a much longer path, I would say that's going to be the comment. So then what I want to do is go and add so what this is going to say is go match this node of type player and then go follow the comments on link to anything that can be there. And then I need a relationship here. This is going to be R2. Right. Whenever you get there, cross any relationship and go to something of type fan. And return that. What did I do wrong here? Selected white space or one too many comments. Variable ends not defined. So it's going to be PR. It's going to be PRC R2, comma F. All right, so you can see Dustin Pedroia has 2 comments, and it shows the fans. So that basically gives you the answer. So I'm just going to copy that. It's easier to just do the raw cipher query. So I'm just going to basically go the Q is equal to, and this, if you remember, there's that weird %S thing that you can do with SQL statements. The corresponding one in cipher is curly braces. And so then I just say result is equal to self dot graph dot run of the query. And I set the PID is equal to the player ID. And then I return R. And so that's going to run the query and return whatever it did. So if I go back over here and comment this out, I have a test get player comments. I'm just going to go and put whatever Dustin Pedroia was in here. So it's going to be this thing. So I'm going to go get the player comments on Dustin Pedroia. I'm going to do a couple of things here, which is I'm just going to print G. And then I'm going to call that. And then you can see I've printed again. So I'm going to go test get the player comments. And we'll try running it. And so this is what I get back is the player, the comment, and who it was by. So there were 2 entries. It's a list. This is the first comment, and that's the second comment. You'll notice over here, however, that I get back this weird cursor object. And the reason is that this is the cipher equivalent of the DB MySQL cursor. And overly simplistically, this call data says fetch all and then convert it to a JSON data structure. If you didn't want to do that, you could just basically do this, which is for R in G, print R, We'll just run it again. So when you go back up here, so, all right, I don't even know what happened here. If you don't want to do two data, you can just basically do two table and then run it. And it just gives it to you in a slightly different format. But you will get back in Pi2 Neo a weird data structure. So just do two data and then print out what it shows and you're all set. Okay. If you want to do get sub comments, get team comments is literally exactly the same. So I'm just going to have, it's going to be the T is a team, team ID is TID. It starts with a team, and I'm just going to convert it to player ID. Okay. That's the team ID. So it's got to be match a team, comment on, that'll be the comment, another relationship fan, run that. And then if we go back over here, I don't know whether I did get team comments. All right, so we'll just basically do get team comments. Test get team comments. Team is Boston. And G get data. So now we'll just do get. Okay, when you were, so you're coming in over the conference room speakers. And when you were telling me that I was making mistakes, it was roughly like God was correcting my programming. And it was really unsettling. Now it sounds like God is photographing us. And when you were correcting my code, I didn't think it could get any creepier, but I was wrong. So if you're not actively talking, please go on mute. All right. So test get team comments. Oh, so there were no comments on Boston. Okay. This wasn't rocket science. There's a microphone on your Zoom thing. You click on it, and I'm not going to have to go get team comments. God didn't tell me to fix this. All right. So you are omnipotent, but you don't pay attention on the team. Relationship object match has no. So what did I do wrong here? Turn R. So it is team ID, comment on CR2 fan, should be exactly the same. Team comments Boston, print G. Why is it a relationship match? Oh, because I'm an idiot and R is in here, so that was really not a good plan. So we'll call this X. So team relationship comment relationship fan. I have no idea why that's coming back that way. Shouldn't do that. Anyway, you can fix this later. You don't need to do both of them because they're both obviously exactly the same. And so if you just did get player, it would be fine. So I'm just gonna pause for a minute. So you can go and take the family photograph of get player comments. So anybody who wants to take the family photograph. And then if you want to go that's the family photograph of sub comment. You can take the family photograph of sub comment. And then it's the same thing, family photograph of comment. All right. Okay, so we will now take a break, and we will then start doing the homework, okay? Sorry, start doing the final. Sorry about that. So let's just take a 5-minute break. That's your favorite. All right, it's game time. Let's go. It's game time. Let's go. All right, so basically what I do in the recitations is I go through the questions until I run out of time, and then in the next recitation, I pick up where I left off. Last time I managed to get to the end, so now we're going to go back and start to the beginning. All the setup stuff is pretty clear. I have given you a link on CourseWorks to the classic CARS database schema. I think there's a diagram in here somewhere. It was in the lecture notes, I believe, but if you do this is an explanation, comes from a MySQL tutorial. This is an explanation of what's in that database. You'll see why in a bit, why we do it, but I installed this and then I exported the database, and you've got an SQL file that you can just download and run to import the data. There we go. So you could download it from CourseWorks, but there's an explanation of what's in there, just in case you're curious. It's a reasonable representation of like what's in a small company. I went through this in class on Friday, so I also discussed, so you can look at the video if you want. You will also have to install the MySQL Sequela sample database. This is the standard sample. You actually have the option of installing this when you install MySQL. I don't do it anymore. This Sequela DB, you can go online and see it. It's got 4 broad areas. There's information about customers. There's information about movies and who's in the movies. There's a bunch of stored procedures and views. And then there's information about what's in a store. This database model is simulating a video rental store. There is now one of them left in the United States, in Oregon. However, when I was your age, this was leading edge technology. So at some point, when I'm teaching this course, I'm actually going to get to the point where I hit students who don't know what a video rental store is. They understand the words, but that's how old this schema is. There's a lot of documentation on it, but installing it's pretty straightforward. And then you're going to have to create a new schema W4111 final to solve a couple of the problems. You're going to put your own data in that. So there's a bunch of environment test stuff. All right. So you can just go through and run it. Make sure the environment's set up properly. This is a subset of the code that I gave you from Neo4j. You can use any code from Hw4 you want in Neo4j questions, including the answers that I gave you in a recitation. So you can use any code you want. And this call here is querying the graph in the movie database, the movie graph. So if you have not installed the movie graph, this will fail. And then this just tests Redis connectivity. So now I'm just going to test Redis connectivity. All right. Step one is returning JSON data. And there's really two parts to this one. The first one is kind of an icky query. So this is the kind of icky query. So go back into the other one. So this is kind of the icky query. What it is trying to do is, if you read the setup, returning JSON is extremely common, especially in web applications. So I'm asking you to return a JSON object. And specifically, I'm asking you to return the core information about an order. So if somebody gives you an order ID, you're returning the core information about the order. You have to match exactly the JSON that I gave you, and you can only use one SQL statement. If you look at the JSON that I give you, there's a header section to it. What's the customer name? What's the customer number? What's the order name? What's the order date? And then for everything in the order, there is like, what's its number in the order? This is called a line item number. What's the product code? What's the name of the product? How many were ordered? And what's the unit price? There's just a bunch of those. Now, if you think about it, if you had a piece of paper with an order, like you filled out an order manually on a piece of paper, it would sort of look like this. There's kind of a header section, which are the things that are properties of the order. And then there's a line in the order form for each of the entries in the order. So it's kind of what you expect an order to look like. So this is the query. Now, what is this query doing? If I go back and I go take a look at the classic cars database, when I pull an order, I get the order number, the date, the required date, the ship date. I'd put the status on here and other stuff. But I would then have to go and join that with order details. So the first problem that I have making this look good for people is if I just run this query, so I'm just going to run this query, and I'm going to return the result. So I'm just going to set that up, run it, and then I go run this. Test SQL, test SQL1, get order. Connection's not defined, so CNX is equal to get new connection. Run again. And see what I actually get back is a list, but everything on the list has got the order number. So the header information is repeated over and over again. That's not what I want. I only want it once. The second thing you'll notice that would be kind of annoying when you go back and take a look at the schema is that when I have a line item, I have the product code, but I don't have the name of the product. You kind of would expect to see the name because I don't remember, all of the product codes. And so I want to show the order header stuff once. And then when I'm showing an order detail, I want to go look the product code up and get the product name, not just star the product code. And then the final thing is I have the customer number, but it's nice to show the customer name. And so I'm going to take the customer number and look it up. And so this query is, let me get rid of that one because I don't think I need it. This query is saying, core of this is joining order and order details on the order number. So I'm going to just basically join order and order details. Some of the stuff in the header comes directly from orders, but I'm gonna go and look the customer information up. So I'm going to do a subquery to look it up in the customer table. And for every order detail, I'm going to do a subquery and look the product name up based on the product code. And so all this is really doing is just cleaning this up a little bit so it looks more intuitive to the person. And I'm not just giving them a table with a bunch of codes and stuff in it. Right? So we'll just go run this again. All right, so they can see that's not quite right. So the solution to that is you write a little bit of code on top of this, which is if I got a result, so if I'm here, if I got a non-empty list, go to the first entry and go pull out the comment stuff. Customer name, customer number, order date. Put that at the top. And then for everything in the order, go add an entry to a list, which are the line item details. So now I'm going to go through the result. This is the information that's specific to that order detail. Go put that in a list. So from the first one, get the header information, and then go through all of them, take the columns that are specific to the order, stick it in, and return the result. So that's how you get that. Okay, so I've got to run, final, we've got to return final result. So we go run this, and we go run that. So you can see it actually looks a little more intuitive. So this is an extraordinarily common thing to have to do when you're writing an application. Is the relational model is very powerful, but joins are often implying containment. but people display containment differently in types like JSON. So we can, this is part one of the family photo if you want to take it. Part two of the family photo. And then the answers in the notebook. I've mentioned this in the previous recitations. I think it was Friday night, one of the students in the class, as I was going through it, said, "Will you post this for us?" And I said, "You want me to post the answers to the final in addition to the final?" And he thought about it and said, "Yeah, that seems kind of unreasonable." On the other hand, I'm trying to teach you a concept, and this is an incredibly common concept. And I don't want you struggling and getting bogged down in the details of aliasing fields and where does the subselect go. So I show you the photograph so you understand the concept. If I just gave you the code, you would just give it back to me. And if we were going to do that, the recitations could be really short. But if you've got a photograph of it, you'll go back and type it in, and it just kind of reinforces the learning. So that's why I just give you the photograph instead of the code. It's just so that you kind of take one more pass through it. On one of the less than courteous posts on Piazza, somebody vented that they spent 30 hours trying to figure something out. And on several occasions, I've said explicitly, don't spend 30 hours trying to figure something out. I don't want you spending 30 hours trying to figure this out just to pick up this simple, common approach. But on the other hand, I want you to have at least done it once. And so that's why I do that weird thing with taking pictures of the code. All right. Number two, player price performance. In homework 5, we basically realized that if we can predict a team's performance based on the aggregate team statistics, we can then try and go and find players, put them on a team, sum up the individual players' performance, that'll tell us the team performance, and then we can go and try and figure out how to build a good team. The problem with that, there's two big problems with that. The first one is, oh, this person hit 30 home runs. Is that good or bad? Well, in general, that's also a property of how much you're paying the person. So 30 home runs is pretty good, but if they're the most expensive player in baseball, maybe it's not worth it. So problem number one is to compute the price performance, not the aggregate performance. So what we're going to do here is we're going to bring the salary into consideration. And then the second one is you can't have a team that only has left fielders on it. You need pitchers, you need catchers, you need other positions. And so we would also have to go and figure out which players can play which position. So instead of doing that for all the positions, we're just going to focus on catchers. So now, nowhere does it tell us in the database who's a catcher. What it tells us is in fielding, it gives us information if that person played as a catcher. So there'll be a record in the fielding table with pos equal quote C. So if you go back into the Laman database, you say select star from Laman 2017.fielding where pos equal, right? We do that. Okay, fine. On the other hand, if you go back in here and take a look, as a field games, I'm not going to consider a guy who played catcher for one game as a catcher. I'm going to consider him somebody who was very unlucky for a day and just like they ran out of catchers that day. And so like they ran out of catchers, and so they picked a guy they don't like and made him a catcher because being a catcher is a miserable job. The canonical example of this is Ted Williams pitched 6 innings in 1945. Ted Williams was not a pitcher. Apparently they were bored that day. I don't know. So I'm going to make a rule that determines whether or not this guy, you can actually go back and do it. Right. I'm going to scroll through this. Right. This guy here caught 1/3 of an inning once. So literally he was a catcher for 1 out. So I don't consider him a catcher just because he caught for 1 out. So I'm going to go make a rule that says the column in outs defines for how many outs you played that position. So there were 3 outs in an inning. 1 guy played for 1 out. There's 27 outs per side in a game. So if over a person's career for position C, if I sum the number of inning outs and divide by 27, that approximates the effective number of games they played as a catcher. So my rule is I'm only going to consider fielding entries after 1950 and only for people whose career sum of in-outs as a catcher divided by 27 is greater than 162, which means they effectively played for a season as a catcher. So those are the only people that are going to qualify as catcher. And then offensive metrics, we're going to have total hits, total at-bats, and batting average comes from batting. And then I'm going to get the information from fielding, which I list, and then I'm going to get salary. But I'm also going to exclude people for whom I don't have 3 years of salary information. Because if I have less than 3 years of salary information, I don't really know what that person's average salary is. So I'm going to go get the average. So again, this is something that is incredibly common in databases, which is you get these things at the periphery, these events or facts at the periphery, but you want to filter them out because you think they're anomalies. So the fact that Ted Williams pitched 6 innings once is an anomaly. He's not a pitcher. And so what I'm trying to do here is focus on data that I believe in some way is reliable or has enough data points that there's some meaning. And so those are the rules that you go through. And then we're going to say, I'm going to evaluate these people. I'm going to take their batting average divided by their salary and multiply that by 10,000 so the number's not tiny. And that's your batting average per dollar. So query for that. Is that. So we'll copy it over. So this is the query. It's a relatively complicated query, obviously. I'll pause for a second to allow you to, once again, take your family photographs. So that's the first part of the family photograph. Second part of the family photograph. So sometimes when students come to office hours and they ask, how did you ever figure that query out? I show them this. Why, yes, I am a wizard. I show this to my family when I fix their computer just because it annoys the hell out of them. I'm really not a wizard. I just know a lot of tricks. So let me just show you a couple of tricks. I don't expect you to necessarily do this on the final unless you want to. But if you notice, there's 3 derived tables here. Right? So there's A, there's B, and there's, you can't really see it because there's C, which is those 2 things joined, and then there's D. Well, let's go take a look at this first one. This is the one that's trying to figure out the salary. And so I don't have to type it over again. What I would do is I'd break that down as a discrete task. I asked you to go figure out something about based on salaries. And so I would not worry about the rest of the query, and I would just go do this. And I would say, select player ID, rounding of the average salary as average salary, count of star as salary seasons, from Lahman 2017 salaries. I have to group it by player ID because I'm doing an aggregate operator, and only consider those people who have had at least 3 seasons of data. So if you go back, that's literally what I'm saying. Go find, only consider players who have played for more than 3 seasons. And so if I go run that, that's part of the answer. So I broke it down. So what I'm just going to do now for the heck of it is I'm just going to go create temporary table T salary as that select. In standard, the most common way when you think about SQL, there's 2 types of tables, a base table and a derived table. A derived table is the intermediate result of a query. So that's a derived table. The way you know that is that if you don't put the ASD there, it binds and says every derived table must have an alias. But you computed a derived table. Another type of table is a temporary table. A temporary table is almost just like a regular table, except when you log off, they delete it. So it's not a permanent part of the schema. So if I just go do this, it tells me, hey, yeah, I made the table. So now I can just go down here and say select star. T salary. Okay. So just go run that and it gives me the answer back. So I just kind of, it's almost like creating a view. I just made a copy of it because views don't go away when you log off. These things do. So now I'm just going to go back over here and play the same game. I asked you to compute something about catchers and what makes somebody a catcher. Well, just focus on that particular part of it. Player ID, the sum of in-outs is total outs. The sum of games started is total games. I didn't ask you to do that. Sum of games is games. Round sum of in-outs divided by 27 as computed games. From Lahman 27 fielding. Only for catchers after 1950. Group it by player ID. So that's basically going to, for everyone who ever caught, it's going to group it. And then I only want the ones where the number of games is greater than 162. So if I go run this, it's going to give me the answer. And then I can play the same thing, which is create temporary table T catching. And I go run that. All right. And it made it. So now if I want to put those two things together, all I need to do is just go select star from T catcher, join T salary on TC dot player ID is equal to T salary dot player ID. I put a semicolon here. And I go run that. And so what I do is every instruction or everything I need to think about, so you can see I gave you a bunch of instructions here. I go make a subtable, a temporary table. So that I did salary, that I did fielding, that I did batting. I could make a third table, which is joining those two. Then go make a fourth table, which is this one, and join that with the temporary table. And so I work it out one complex thing at a time. And then basically when I'm done, I just need to go back in and repeat what I did, but put derived tables where the temporary tables are. Because I can get a correct answer and verify it at each step, and then just assemble those together. Whereas if you try and write this thing from scratch, it's just a nightmare. And so that's how I write these things, is I go and figure out what's actually being asked, and then go make temporary tables for each of the kind of sets of things that are being asked, and then go figure out how to put all the pieces together. So I just wanted you to see that that's how I do these things, because these queries can be staggeringly complicated. So if I haven't, I don't know, if I allowed you the family photograph yet? Do you need to take the family photograph? All right. So the new connection, and I just wanted to screw around with pandas. So new connection, and then I'm going to say my data frame is pandas read SQL. I give you the query and the connection. So then I have to go make it. All right. Run it. Oh, it's the hell is going on? Get new connection? Need to find get new connection. What is there? So I'm in the wrong notebook? Yeah. Yeah, so just gonna run it here. The query goes here. Try it again. All right, so it ran, get the first 10. So I'm just dumping the data frame out. As far as I'm concerned, if you don't need the new data frames, if you got a table that looks something like that, I'm fine. Typically what happens after this at this point is you would then use pandas to do things like compute the batting average and sort it. And so I just go run that. So you can see that the player with the highest career batting average as a catcher is a guy named Hw4. He played effectively almost 1,000 games as a catcher, which is a lot actually. So he played about 900. That's a really good career batting average, especially for a catcher. But on the other hand, if I go look at it, he also, because he was a good catcher, he made a lot of money. And so if you go look at the price performance of a catcher, this guy's got the best price performance. A 200 batting average is slightly better than my grandmother could do, and she's dead. But on the other hand, he was dirt cheap. All right. And so somebody had a question in the meeting. This is a question about Hw4. No idea what that comment means. So we'll worry about that one later. So really it's just this query. And this does lots of the things that you do in queries. So I did this one because it does joins, subqueries, group by, and having. That's the reason I do that one. And also, just to show you that little trick about how to write complex queries is break it down into the discrete steps, then go build the answer from the discrete steps. Okay. Are you done pictures? Do you want a movie or? All right, so that's that question. All right. Shaping data for business intelligence. Online transaction processing and similar applications have relatively simple reads, and they create and update delete. So I'm gonna go get my travel itinerary and make a change. I'm gonna go get all of the students' homeworks and assign a grade. I'm gonna find a product in a catalog and add it to a shopping cart. Data access characteristics. The data access characteristics of these are, because it's doing create, retrieve, so because it's doing insert, delete, and update, referential integrity is important. When referential integrity is important, that causes you to want to normalize the schema. So it causes you to want to remove functional dependencies, because functional dependencies cause update anomalies. And because they're relatively simple, and it's the same thing over and over again, like I'm checking my bank account, I'm looking for an itinerary, you can anticipate the join paths, and the on conditions are usually just simple keys. So that access pattern causes it to be okay to normalize and decompose. Decision support requires complex multi-table joins. You're frequently computing derived columns. There's a lot of aggregation and summary. Joins are bad. And so the design here is big, wide, denormalized tables and pre-computing all the joins. So instead of doing views, which computes the join every time the question is asked, you build a copy table that's denormalized, or you do the aggregations and the summaries. So OLTP leads you to normalized forms. These are the various normalized forms. Decision support leads you to big wide tables. So the motivation for this is when discussing Moneyball, we discussed figuring out wins as a function of the team metrics. Team's a combination of players, and the individual player's performance aggregated determines the team's performance. A player's performance is spread over several tables: salary, batting, fielding, pitching, appearances. We're going to produce a table that summarizes a player's performance metrics. We're going to look at the following ones: games, at bats, runs, hits, doubles, triples, home runs, runs batted in, walks, bases on balls and hit by pitch. There may be pitching information: game, wins, losses, for how many outs did they get as a pitcher, hits against them and earned run, and then fielding. The problem is I want a single row that summarizes a player. Players played multiple positions. The fielding table is going to have an entry for each position. I want to get this into one row. So what I want to do is I want to say I want games, outs, attempts, and errors for the player as a whole. Then I want to break it down by the infield positions, then outfield, then catcher, and then pitcher. So I need to convert potentially 9 rows of fielding information into one. So I'm taking a bunch of columns and stapling them at the end. We will ignore salary and appearances. We'll ignore seasons prior to 2010. Do not include batting information for a batter with less than 500 career at-bats. Do not include pitching information for a season with less than 50 IP outs. So pitcher didn't really pitch in a season if they didn't get 50 outs. Ignore them as a pitcher if they have less than 150 career outs. And don't include fielding information for player that had less than 50 outs at a position in a season or 150 in his career. Produce the summary table. This should be a copy table. You can create intermediate tables, so you can do that weird temporary table thing I did. You can create your temporary tables using the create table XXS select. Just show all of your create statements. This is the answer. So you can see player, right? Games as batting, at bats, runs, hits, doubles, triples, home runs, runs batted in, walks, intentional walks. This person never pitched. And then we keep going over here. All outs, all attempts, all errors. Infield games, outs as an infielder, attempts as an infielder, errors as an infielder, and they never played outfield and they never pitched. And so this has summarized everything I need to know about the player on one line. And so then I can then start taking various of these records and trying to build teams because I just know the aggregate information, right? If I actually got this answer correct, it was kind of a holiday miracle. So how did I try and accomplish this? This is the flow that I used to do this. Whoops. Right, so this is the raw schema. I ran 3 queries to create temporary tables. One that computes aggregate batting. So I filter people out who have not had enough at-bats, and then I go create their career summaries and write that to a summary table. I do the same thing for pitching, and I do the same thing for fielding. The problem is that I'm going to have one pitching tuple for a person's career, one batting tuple for a person's career, one pitching tuple for a person's career. But this one, in theory, could have 9 career entries for a person. I don't want 9, I want 1. Right. So the first thing I'm going to do is I'm going to take, and I'm just going to go and group it by the infield positions. So this table is going to have one career summary thing, but just for the infield positions. So I basically went through and said first base, second base, third base, shortstop, grouped by that. So that's taken 4 of them and flattened it to 1. So now what I'm going to do is I'm going to take this table and I'm going to left join it with that one. And then I'm going to drop some stuff. So at this point, I've added at the end of the row the infield stuff. So that is all fielding and infield. And then I do the same thing over here, which is I go and I pull in outfield. So I do a left join, and now that's going to give me career, infield, outfield. Then I do the same thing for pitching, and then I do the same thing for catching. And when I'm done, I've flattened all the rows. So now I have the fielding part of this. I join batting and pitching, and then I join that with fielding, and that's the answer. So go write that SQL script. Just kidding. This is the SQL script. So put your cameras in movie mode. So no, that'd be insane to ask you to do that. Even I'm not that crazy. So all I really want you to do is forget all the fielding stuff. Compute the aggregate pitching based on batting based on the rules, the aggregate pitching. You can make 2 temporary tables, join those, and that's the answer. So you just need to do this part. And remember, this is actually what I wrote. So somewhere down in here are those steps. So each create table statement in here corresponds to something in this graph. So all you really need to do is to go find these 3 query statements. And the easiest one, obviously, that's clearly the batting one. So create table batting summary final as select player ID, sum of games, sum of at-bats, sum of runs, sum of hits, sum of doubles, triples, home runs, runs batted in, walks, intentional walks from batting where the years after 2010 only consider a season that had more than 100 at-bats, group it by player, and only include players that have more than 500 career at-bats. That produces this one. Now, the reason that I went through this is in the last lecture, I talked about extract, transform, load flows. I talked about MapReduce stuff. This is a somewhat contrived example, but this is what an extract, transform, load flow might look like, which is these are extracts, right? And then transform. And so you can sort of see extract and transform, extract and transform. And so this is a somewhat contrived example, but this is what a MapReduce job with some data you're familiar with. So that's why I did that. You only need to do a small part of it, right? And so, and I've given you the subqueries. And so they're easy to find. They tend to be the first 3. So it's this one, create the batting summary, create the pitching summary, and then somewhere down here, I'm going to join those. It's right here. Create the batting and the pitching summary. Now this one's got to be a full outer join because I want information about the player. They might have batted, they might have pitched, they might have done both. And so the last one is this one, which is a full outer join. And so it's that one. It's the create B_P_ summary. That's basically the answer. And so you can just go in and play with those ones. Is that clear? And that query is this query, so you don't really need a photograph, but the photographs can tell you which ones I'm talking about. But this statement is actually in the final notebook that I gave you, so you can just cut and paste it from there. Schema refinement. So can I move on? Is everyone clear on that? Outstanding. The table definitions for classic car orders detail and classic cars products are below. For the purposes of this question, do not consider any other tables or relationships except for these two. There are several design flaws with these two tables. And if you probe on it, it'll reveal some more. So this request is produce an improved, cleaned up schema for just those two tables. Your answer probably should include a trigger or triggers. Normally, if you're trying to protect data integrity, you put a trigger on insert, update, and delete, so 3 different triggers. You only need to worry about an insert trigger. Do not worry about the other 2. And do not ask me how many improvements I want you to make, because if you have a job and your manager asks you to fix a defective schema, I don't think the answer, how many improvements do you want me to make, is the answer your manager is looking for. Because the answer is going to be all of them. So let's go take a look at this. All right. Order number looks okay. Product code probably kind of looks okay. Quantity order, price each. So the types and the not null seem pretty good. What I would do on this one is, the minimum I would do is I would write an insert trigger, which is the quantity ordered can't be -17. So my insert trigger would make it be at least 1. The price can't be negative. And the order line number's got to be an integer. So that's some stuff I would do in the trigger. And the product code is clearly a foreign key into the product table. So these are kind of okay with type and not null. But I would go and make sure that people didn't enter junk data with a trigger. And then do a foreign code, foreign key. This one's more interesting. Product code, product name, product line. Let's go take a look at product line. So basically, if I go down here and I do %SQL select distinct product line from classic cars dot product to products. So go run this query. Call classic car. So what do I call it? Classic cars.
It's a double C.
It's a double C. Yeah. Thanks. You can see that there's only 7 product lines. That's clearly an enum. Now the type in the database is var car something, but that is clearly an enum. So I would go in and I would set product line to an enum. If you go to product scale and you do the same thing for product scale, that's clearly also an enum. And so two fixes to this are product line and product scale are enums. Quantity in stock, buy price, quantity in stock, buy price, and manufactured suggested retail price clearly can't be less than 0 or less than 0. Quantity in stock could be. And so the obvious cleanups to this one are a couple of triggers to make sure you're not setting negative values, a foreign key relationship between order details and products, and a couple of enums. And those are the clear ones for this, right? So all you really need to do is just put your DDL statements when you've cleaned it up. That one should be relatively quick. SQL modeling inheritance. A person has the following properties: uni, last name, first name, and email. A student is a person and has the additional property of major. A faculty is a person and has the additional property title, like professor. No one is both a student and a faculty. In all instances of person are either a student or a faculty. There's no third kind of person. Define a SQL schema for representing person, student, faculty, and an advises relationship. Draw a simple diagram. Now you then must write several functions, probably in Python, to create a student. It's going to compute a uni based on the first two letters of the first and last name and a count of a number of people that already have that prefix. And you're going to retrieve a person and a student. And some of these may require transactions. Do not do triggers or stored procedures. Do this all in Python. So this is my schema. Create table, person. I did a 3-table solution. Uni, last name, first name, and email. They're not null. Uni is a primary key. Email must be unique. So it's a unique constraint. Student is a uni because I need to find the person and the major, and advises, and I said every student must have an advisor, so that's not null. Primary key, there's a student key that's created because there's a foreign key relationship. So there's a foreign key relationship from student to person and from student to faculty. And then faculty is basically the same, only the only foreign key relationship is hub. So that's basically the schema. If I go back down here, this is what my schema looks like. All I did is define it and then reverse engineer it in MySQL. And that's kind of what it looks like. So you can take a photo of that if you want, which is there's a person, a faculty. So if I have a faculty record, it must go to a person. If I have a student record, it must go to a person. The other end is 0 or more. Because just because you're a person doesn't mean you're a faculty. Vice versa. Now the problem with this is, actually I think this is wrong now that I think about it, but probably should be 0 or 1. So that's probably wrong. The problem is, I'm gonna do this. It's one of these things. these things again. That's not it. That's not the public one. So I have to go to it in PowerPoint. Open recent. I'm gonna make this bigger. No, I didn't do it for that one, that's why. There's a couple of weird things here that you can't actually do. So I drew this arrow. So I had to add this manually because it doesn't really show inheritance. So I'm just sort of showing an inheritance here. But the other thing that you can't actually do in this is if I make this 0 or more, or I make this, the correct answer to this is 0 or 1, that's a mistake. It's like the third time I've gone through it and I just caught it. That should be 0 or 1. The problem is, if you're a person, you don't necessarily have a faculty because you might be a student. If you're a person, you might not have a student, you might be a faculty. So both of these have to be 0 or 1. However, only one of them can be null. You have to be either a student or a person. There's no way to draw that in an ER diagram. And so that's what's being, there are two things that you can't draw in an ER diagram. The inheritance and the fact that this weird thing is happening, which is you are either a student or a faculty, but not both. So exactly one of these is 1 and the other one's always 0. All right. And I just repeat the code, repeat the run queue. Now, you'll notice that I told you, you must create a student. So you must create a student, retrieve a person, and retrieve a student. What is implied by the fact that I told you to create a student? What's missing? I didn't tell you to do this, but because this relationship is required, you have to make a faculty before you make a student. Because if there's no faculty member, there's no advisor. Therefore, you can't make a student. So implied by this is the fact that you must also implement create faculty. Because if you don't do that, you can't make a student because there's a mandatory foreign key relationship. So this is just a bunch of helper code. I wrote a simple function, compute uni prefix. And what that does is it has last name, first name, just takes the first two characters, staples them together. That's going to be the prefix. So in my case, that would be FED0. And then I'm going to go make create faculty. I'm going to get a connection. I'm going to get a cursor. And then I'm going to set the isolation state as serializable. Because I'm doing things that require a transaction. So the first thing I'm going to do is I'm going to compute the uni prefix. So that's going to give me, in my case, FED0. And then I'm going to go and say select count of star as count from person where the uni is like the prefix. And so that's going to tell me how many unis in total have that prefix. So then the next uni for this person is clearly that plus 1. And then I'm going to go and insert into the person, because I needed to compute the uni before I could do the insert. The reason I did a transaction is I read something and then I'm going to write it. If I have not locked it, somebody else could write it while in between my reading it and writing it. So I could overwrite it. So if two of these are running at the same time, they have the same prefix, right? They're both going to get 7. One of them is going to write 8. The next one's going to write 8. There'll be 2 records in there with 8. That's not the right answer. And so I have to lock this thing because I'm going to write it. And then I also have, so that is why I need the isolation level. And I need it to be atomic because I'm updating 2 tables. I'm putting a row in person and a row in student. Those both have to happen or neither of them have to happen. So the reason you need a transaction for faculty is this needs isolation, otherwise you'll get the unicount wrong. And this requires atomicity. Those both have to happen or neither happens. And so if you get here it worked, you commit and close. If there was an exception, you roll back. So that's how you make a faculty. We'll take the family photograph if you want. Are you waving? Do you have a question? Sure.
Can you explain the 4%?
All right, so I'm doing an insert. There are 4 columns: uni, last name, first name, email. So that's a query template. The way that works is this is the query. Those are the values to insert into it. That's just the way you represent query parameters in MySQL strings. That's all it's doing. Any other questions? You all got the photo? Student is almost exactly the same, which is I give you last name, first name, email, major, and advisor. Get a connection, get a cursor, set the transaction level to serializable, compute the uni prefix, go count how many uni prefixes there are that match that, add 1, and then go insert into person. And then I go insert into student. Now notice I don't have to check that the advisor exists, because if the advisor uni is not there, this will get a referential integrity error. An exception will happen and I roll back. So I don't actually need to check that the professor's there, because the database will do that for me. So it's literally the same as create faculty. Retrieve person. I just go pull the data. So it doesn't need to be transactional. So I just go get the data, run the query, return the answer. And retrieve student is pretty much the same, only I have to join person and student to get all the properties. So a lot of this is actually in one of the lectures. I did some of this in stored procedures, but this is just doing it in Python. So everybody good with that? All right. There's a bunch of tests. Graph database.
I'm more interested in how one majors in that.
You need a note from your advisor. Or your pre-law, one of the two. Everybody good? All right. I don't know what it's like now, but when I was in Columbia College, those of us that weren't pre-med and pre-law hated the pre-med and the pre-law. I don't know what it's like now, but I absolutely hated them. It was almost like it was almost like 3 undergraduate classes, the pre-law, the pre-med, and then the rest of us. It was really weird. Neo4j database, exactly the same. Problem statement's exactly the same as for the SQL one. Draw a diagram of your model. and do the same functions. You don't have to do transactions if you don't want to. This is my diagram. It's a little hard to see what's actually going on here, but if I select FED01, in the bottom, it shows me that that node is both a faculty and a person. So you don't use two tables. A node in a graph database usually has more than one label. So unlike relational, where you've got records in two tables, there is a single entry, there's a single node for the person, and it's labeled based on what types it is. So that is the fundamental difference, is that you don't have to worry about multiple different sets of nodes. It's done via labeling. That was the query that produced this. But anyway, so that's kind of the model. This is a bunch of the utility code fan graph. Create faculty. Self, last name, first name, email, title, just like before. Compute the uni prefix. I convert it to lowercase because unlike MySQL, string comparison is case sensitive in Neo. So FED0, it's case sensitive. So I convert it to lower. I begin a transaction anyway. And then I run this statement. Match all of the nodes with label person. They could also be faculty, student, wizard. So match all the people. Where the uni starts with the prefix. So I'm going to pass the prefix in. So where the uni starts with this and return the number as count. Run that query, get the count. That's the next uni. So I then go make a node. The node's got two labels, person and faculty. And then it sets the properties. So all the properties are in one node. They're not in two tables, and it's got labels. I create the node and I commit it. Now, in this one, I have to do get faculty because referential integrity constraints are kind of odd and inefficient in a graph database. So I have to be able to go and find a faculty. So find nodes by template. That's one of the helper functions I gave you. Label is faculty, and this is the uni. Did I get something? So that's literally like get player or get anything else. Now to create a student. Compute the uni prefix. Begin a transaction. Do the same match thing. So this is exactly the same. This is actually really bad code. This should be moved out into a separate function. Shouldn't be repeated like this, but I put it in here so it's just clear. So that's going to compute the uni. Then I need to check that the advisor is there because I don't have a referential integrity constraint. I can't rely on the database getting it right for me. And so I check. If I find all of that, I'm good to go. I make the student, the labels person and student. I put all the properties in, and then I make a relationship advises from the faculty to the student, and then commit it. And so that's how that gets set up. There are really no foreign keys. So I've got to check that the target of the relationship exists. And to build the relationship, I have to go and set foreign keys as relationships. Now on get person, I only want the personness of this. But remember, I don't actually have a person table or a node that's just a person. All of my nodes are many things. So if I get a person that's a student, I get all of it. So what I did is I said, person fields, these are the fields that make up a person. I'm going to find the node by template. So did I find a person with that uni, or I find a node with that uni? Remember, that's going to give me back all of them. So I'm basically going to say, what are the property keys? So what are the fields that are actually in the thing that I got back? And if that field is not in person fields, delete it. So I might have got back something that's got student fields and a bunch of other stuff. I'm just getting and deleting everything that's not a property of a person. There's other ways to do this, but I just didn't want to go and write custom cipher. So I'm basically saying, like, give me this thing, and then I'm just not going to return everything that isn't part of person, and get student. So you can just take those two photos if you want. All right, and then there's a bunch of tests in here. Redis. Do the same thing for Redis. How you do this in Redis, no one would ever really do it this way. But it is a pattern that people use periodically. So if I do keys, oops, that's going to give me all the keys that match a template. The way I represent that one of the pieces of data in my database represents a person and then a faculty is by the key. So that's the uni, right? But this little prefix here, which is just a convention, says that this is a person and a faculty. So if I wanted to get all the faculty, what did I do wrong here? Person, faculty. So I did something wrong here. I don't know what I did anymore. Oh, basically, that doesn't work. You have to do this. That gives you the keys of the people that are faculty, and then you'd write a loop to go get the data. If I want to do the same thing for just people, those are all of the things that are people. So I'm going to get back a list of the keys, and then I'd have to go through and pull the records out individually. So that's the convention for how to handle this kind of thing in Redis. It's not used commonly, but it helps highlight the difference between a graph database, a key value store, and relational. So that's the pattern. It is common enough that there's a tool I use called Redis Commander. So it's just basically a browser interface. You can see that it implements this pattern, and it basically will say everything before a colon is a branch. There are 3 things in that branch. The next branch is faculty. There's 1 thing in that. And so it's almost like a taxonomy. And so you're using key prefixes to sort of put things in a taxonomy. It's a common design pattern, and it's so common that Redis commander understands it, despite the fact that it's not actually part of Redis, it's just a pattern. And these are called branches. Then you can see that that is something that's attached to a key. So that's how you handle this type of classification. So in a relational database, you handle classification by multiple tables and joins. In a graph database, you handle it by labels. And in a key value store, you handle it by conventions on the key. So that's how you handle classifications in those three databases. And the code to do this is pretty straightforward. Go back and find my final exam. So because the things we're using actually are dictionaries, I went back and I actually turned it back from r.set into hm set. So we are actually setting them as maps, not strings. I did an hm set and then I do an hget all. So I went back and put in the original one. I also, instead of just dorking around with the prefix, I actually compute the prefix and go check. So I gave you a last name and a first name. I'm going to compute the first two characters of the last name, the first two characters of the first name. And then I'm going to say the key that I'm looking for is a person of any type. And it ends with the prefix and then other stuff. So if I go back here and I do keys of person star colon star colon POMA star. There are two people with that prefix. I now know because of the length of the answer, the next uni is 3. And so that's how you use that pattern. And it doesn't care whether what's in the middle, whether it's student, faculty, crazy faculty, whatever. So that's how I get the uni. To create a faculty, I say, go compute the uni. I'm making a person who's a faculty, colon uni, and then go set the properties. So go add it as a map. The reason you do it as a map as opposed to a string is if I do hget it's hmget. I'm going to copy this student. hmget, that's the key. And I say last name, first name. It gives me, so that's how you do what's effectively a project. Is if it's a map, you can ask for just the elements of the map you want. So that's a case where you actually can peek inside of it to do a project. So that's why I converted it back to a map. So if I wanted to do get by template, be a little bit harder, I could do get by primary key and then just get the fields. Anyway, that's create faculty. Create student is almost exactly the same, except I have to put the advises relationship in. There's no easy way to do this. And so I built a separate a separate thing. Advises in a uni is a list of the unis the person advises. So if you go back over here and do L range. Actually, I actually wrote the code. Yeah, get advises. So if I want to find out who this guy advises, who this person advises, I give it the uni. I say go into the advises, add the uni, and return everything in the list. And you can go back into Redis Commander and see it. So if I go into advises, it's an array. And those are the two students that person advises. So that's the overall structure of this, which is the batting. These things are from some other stuff, but the overall structure of this is you've got a person branch, you've got a faculty branch that follows that, you've also got a student branch that follows that, and then the last thing in there are the actual keys, unis, and then there's an advises branch. And that's how you model this kind of thing in a key value store. That's how you model classification in a key value store. Redis is not transactional, so you do not need to worry about starting and stopping transactions. To be more precise, Redis is single threaded. So by and large, you don't have to worry about isolation of a single request. And there is a way to write things that are like stored procedures in Redis. You write them in a scripting language called Lua, L-U-A, Lima Uniform Alpha. So what would happen is if you actually wanted these things to be atomic, you would do them with Lua scripts in the Redis engine as opposed to outside. But that's basically the code for Redis. All right. So we'll go back. So get person. And create student, create faculty is basically the same. Right. All right, so we'll wrap up here. There's a couple more problems. So I'll just pick up here on the recitation tomorrow, which is going to have to be electronic because I can't find a room. All right. All right.